Hello everyone, my name is Ranjit, Application Engineer here with Mirables Design. I would like to welcome you all for today's webinar, Analyze the Energy Harvesting, Consumption and Management using VisualSim Architect. The session is going to be approximately for about 45 minutes and the session is going to be a combination of both presentation and demonstration as well. Before getting started with today's webinar, I would like to go over a few items. And you must be seeing something like this on your desktop, on the right hand side of your desktop. And there is a chat window, and please post in your questions if you come across any. And we have people in standby. They will be answering all your questions. And also I'll be taking up these questions in a Q&A session as well. For those of you just joining us, welcome to today's webinar, and I hope you enjoy this session. Here's a quick outline about today's webinar, and I'll be starting off with trying to understand why system-level energy and power analysis is required, and also I'll be looking at the ways in which how VisualSim can help in understanding and solving power analysis problems and difficulties itself. And then I'll be looking at the ways in which you can harvest energy from photovoltaic cells or from vibration sensors or from motors and things like that, and also how to model load and management capabilities as well. And also I'll be looking at an example around cycle accurate memory power analysis itself. This actually gives you an idea about how detailed models can be constructed using VisualSim and how accurate the power reports can be. For example, these power models of cycle accurate memory are actually nearly 99% accurate as opposed to implementation level models. So for those of you just joining us, I'd like to welcome once again. And if you have not heard about Mirables Design or VisualSim Architect, we are a Silicon Valley-based systems engineering company, and we provide software solutions for architecture exploration, power and performance analysis of electronic systems, semiconductors, and embedded software. The major motivation for conducting these or constructing these simulation models is to conduct timing, power, and functional analysis. And the product itself is called VisualSim Architect, and I'll be using this particular tool during the course of this presentation as well. So why system-level power analysis? This is a kind of major question that most of the people ask all the time. To answer this particular question, we must really look into the details, or we must really look into the challenges that are closely related with system power consumption itself. So if you look at if the power consumption of a particular system is quite high, or it is exceeding the threshold limits, this may actually cause us challenges in terms of not meeting your performance versus power trade-off ratios, what you're expecting. And if the system is actually a battery operated system, then you may actually see a low battery life as well. And also if your power consumption is too high, then it results in generating a lot of heat, and you may have to include a lot of heat sinks to dissipate the heat generated itself. And again, at the end of the day, it results in a huge and bulky system model. So if you look at the kind of problems such as power versus performance trade-off related issues, these issues can be identified and explored at the system level very effectively. For example, these system level models actually enables you to identify the power gains and performance reports with a larger set of design explorations itself. You can run more and more test cases and use cases and workloads on the target platform and change the system configurations and try to see the optimal system architecture that meets your performance as well as power requirements. And also you can able to understand if there are any kind of peak power consumption at a particular timestamp and try to understand why that sudden surge has occurred as well. Okay, so keeping in mind of these criteria or these challenges, we have actually assembled up our simulation model, VisualSim itself. The modeling environment is completely graphical and hierarchical with a large set of stochastic and cycle accurate library blocks. And once the model is constructed, you can actually use these simulation models to conduct architecture exploration, performance analysis, power analysis, and hardware-software partitioning. And the library's blocks are used to assemble hardware, software, network, traffic, reports, and use cases as well. And if you have any kind of models or modules that are already constructed in C, C++, Java, or any algorithms developed in MATLAB or Simulink, you can directly import it to VisualSim and start exploring immediately. And this is a kind of quick overview about the tool itself. And now let's start looking into the power analysis or power exploration capabilities that are available in VisualSim Architect itself. If you look at the power analysis capabilities in VisualSim Architect, so it is actually conducted based on dynamic state activity of each and every component itself. Every time the state of a particular component changes from one state to another, these transition details will be actually monitored and notified, and these information will be utilized to compute peak instantaneous average power consumption of a complete system as well. The input for constructing these power analysis models is actually the power level details for each and every component itself. And that is the only thing that it requires to model the power model for a particular component itself. And apart from that, functional and timing related informations are already available and already modeled for constructing your or for conducting your performance analysis or architecture exploration itself. So in the essence that it is actually you're reusing your simulation models that you have used for architecture exploration and performance analysis to conduct power analysis itself. Or it could be the other way around as well. So you can use a single platform and within a single simulation run, you can monitor both power as well as power performance analysis itself. And if you look at the block diagram over here, it actually, if you consider this, the outer layer of the box, if you consider this as a particular block in VisualSim, it has both functionality and timing information embedded in it. And if you look at the power model for this particular block, every block or most of the blocks are provided with power information as well, or state of that particular block itself. It can go from idle state to active state, or active to standby state, or standby state to wake state, and things like that. You can add additional states based on your requirements as well. And here's the power table setup. And the block or the library that that has been used for conducting power analysis is power table block. And if we double click on that, or if we configure this particular power table block, you must be seeing something like this on your on that particular block itself. It includes a set of components that are available in the simulation model or in the system that you're exploring, and it'll have a list of different states and power consumption values for each and every component as well. And the standard devices supports up to 4 power states, including standby state, idle state, active state, and wait state. And when we say standard devices, these are actually processors, memories, buses, schedulers, servers, and DMA. And the custom blocks, blocks that you actually construct for modeling your custom requirements. For example, you need to have a custom arbiter in your model or a custom router, and you can actually model a custom router using basic building blocks in VisualSim, or you can use a scripting language that we provide along with VisualSim as well, which is 90% equal to C language. And for custom blocks, we actually support up to 12 different power states itself. And the transition cycles that you can see in the last column over here, this is actually utilized to compute the delay to go from one state to another state. Okay, and these informations can be actually imported directly from a text file or from a CSV file itself if the number of components are too many. So how does it really compare with the power analysis with the formal methods or using Excel spreadsheets? And if you look at the power analysis with the Excel spreadsheet in this example over here, here we have a list of components and list of uh, power values for various states itself. And here we have computed an average power consumption for a set of examples or a set of example scenarios. And this actually can give you information on static activity that is happening in the architecture, but it completely fails to capture the dynamic system behavior of a complete system platform itself. So how do we actually provide an alternative solution for this? We actually take your Excel spreadsheet, which actually has power information. We actually integrate that with our simulation model or power manager itself or power table itself. And when we run the simulation model, the Excel spreadsheet information will be actually utilized to update the power information for each and every component itself. And if you look at the graph that we are plotting over here, initially we it started with the power consumption report of 1.19, but but after some time, the power consumption of the complete system started going up. So this could be a kind of problem with the hardware architecture itself, or because of the dynamic behavior of the system platform that you're working with as well. And these kind of problems are very difficult to identify using formal methods or mathematical computations. And this is where actually is dynamic power analysis actually helps you to kind of debug those problems and capture those problems as early as possible in the design process. So how does really VisualSim help in conducting system-level power analysis, or how does power analysis conducted with VisualSim can help you? So one of the crucial things where we actually help the designers is actually to be able to refine the hardware and software architecture itself. You can actually size your processor, size your memories, or select the configuration for your hardware platform itself, or select at which frequency your devices should run with, and what is the voltage scaling that you have to go with, and whether the selected processor or selected memory is going to meet all your requirements in terms of power consumption as well as performance requirements. And with regards to software architecture, we actually help you to be able to kind of map your software applications onto the multi-core and multi-processor platforms to be able to distribute your tasks uniformly between multiple processing units, and to be able to achieve a better performance versus power trade-off scenario itself. Okay, and in addition to that, you can actually quickly check the feasibility of your project itself and the implementation efforts required, and also you can visualize the power consumption of the complete system or subsystem level power consumption as well, which is very crucial for implementation level engineers as well. And also you can try to understand if there is a way to optimize these power consumption, whether it is at system level or subsystem level as well. And definitely these are dynamic simulations, and your simulations with lots and lots of test cases or use cases and workloads increases confidence of your system architecture itself, because you're not just evaluating your system architecture with static power data, but you're actually going beyond it with dynamic power data itself. Okay. So to be able to kind of customize your power consumption models, we actually provide two ways to do it. One is to be able to model your power state machine itself. You can actually define a transition related details for a particular model or for a particular block itself using these finite state machines with a set of guard expressions and things like that. And in addition to that, you can actually use regex expressions that we use. For example, if you want to add battery charge, you can actually use the function called add battery charge. And if you want to move from active state to standby state or standby state to active state of a particular component, I can actually just use this new power level, and I can actually provide what is the power that is actually I'm sorry, if you want to actually provide a new power level for a standby state or active state, you can actually provide that using new power level. If you want to move from one level to another level, you can actually use, for example, from active to standby, you can just go with power update and provide what is a state that you're working with. There are lots and lots of regex expressions that we provide, and I just capture the prominently used expressions over here. At this point, I would like to go to VisualSim to give you a quick idea about how quickly you can construct those simulation models. And I'm going to construct a model right now. And I'll be bringing up the block diagram editor, and I'll bring up the digital simulator. So this actually allows me to run simulations for a given set of time. And then I will just include a traffic generator. So that actually gives me a kind of, or models my workload scenario. And I'll not be modeling very detailed model in this case. And what I'm going to do now is I'm going to add some information such as what is the name of the input source itself. And I'll say sensor 1 or master 1, and I'll say the request size is going to be about 512 bytes of data, and I'm gonna keep it as it is here. And then what I'm gonna do is I'm gonna actually model a kind of arbiter here. So to be able to model the arbiter, what I need is I need a queue over here. So it is a kind of arbiter queue. And then to model the arbitration delay, I just actually insert a arbitration or delay block over here. And to compute what is going to be the delay across my arbiter, what I can do is I can actually utilize a parameter that actually tells me what is going to be the clock speed of my arbiter. So I will say arbiter clock speed, and I will say this is going to be about 200 megahertz. I'm going to connect over here, and in this particular block what I'm going to do is I'm going to compute the arbitration delay itself. So I will say arbiter delay, and this is going to be based on the size of the data that I'm working with, which is actually input.bytes divided by arbiter speed, arbiter clock speed, which is actually 200. So this is going to give me the delay, and I'm going to utilize this field as a delay value. Okay. You can directly provide that delay value as well, but I'm actually making it nice and clean. So what I need to add is, if I consider this complete portion as a arbiter itself, what I'm going to do is I'm going to actually add a power level. So update, and I've not added the power manager yet. I'll be adding it. I'll call a component called arbiter, and I'll be pushing this to active state over here. So once I leave my arbiter, so what I will be doing is I'll be actually changing this power level from active to standby. Okay, so what I need now is I need a power manager or power table. So I need a resource called arbiter. This is my resource which I have here. I'll say this is going to take about 200 milliwatts, and standby is 100, and weight is going to be about 40, and idle is going to be 0.0, and this is going to run for 500, and I'm going to just change this from watts to milliwatts, and this is done. And now I need to connect this up, and I need to kind of make it nice and clean arbiter mode now. So once you send one transaction out, you will be actually sending the second transaction out. Okay, so this actually tells me I'll be actually sending my head of the queue to the output port of my block itself. So this actually completes my modeling. So I can actually extend this to compute my end-to-end latency and things like that. And what I'm going to do now is I'm going to try to capture the instantaneous and average power consumption. These two ports gives me information on instantaneous and average power. I'm going to send every one transaction in and run the model. Okay, so this has completed the model now, and the red plot actually gives me the instantaneous power consumption, whereas the blue one actually giving me the information on instantaneous average power consumption itself. So what I can do now in this very simple example is I can try to change my arbiter clock speed, which actually results in total delay that is going to be taking for the arbiter itself. So I'm going to make this or run this at 100 Mbps. You can actually see the power consumption actually gone up. And if I actually make this or run faster, you can actually see that power consumption actually have dropped up. Okay. And this is how you can actually simply conduct the explorations. And also you have seen that I have used these custom regex expressions to update the power level as well. But in most of the standard blocks, you will not be doing this, and this is automatically added. To give you an example, I'll open up an example over here. Let me think. For example, if you look at this particular multimedia system platform, in this case we have all my hardware architecture element, including processors, accelerators, AXI, and SDRAM. And if you look at the power manager over here, this is actually utilizing the provided the name for each and every component. And as you run through the models, the power consumption or how long you're actually in the processor itself, or how long you're actually waiting for your data from a cache itself and things like that. And based on that, power consumption values will be updated for these simulation models itself. Okay, I'm going to go back to the presentation now. And looking at the energy harvesting library, so we actually provide energy harvester models for light, vibration, motion, pressure, air, and other custom energy harvester models as well. And each energy harvester models includes a certain set of key attributes that includes efficiency of your power generation, and what is going to be the start and stop time for energy generation, and what is the maximum capacity of charge that you can generate, and charge upgrade interval as well. And if you have any kind of power profile trace files, you can also import that into photovoltaic or motor EH, motor energy harvester, or custom energy harvest models as well. And these blocks are linked with power table as well as battery. So it is ready to start up with modeling and connecting with other components as well. And the reports can be generated with includes standard as well as custom. Standard reports such as instantaneous power, average power, or battery degradations and things like that. And if you look at the power versus performance trade-off scenario that I was talking about in a little bit, so this includes, for example, you can have in hardware architecture, including all your hardware architecture elements, including your processors, memories, interconnects, and things like that. And you can have a behavior model that includes or that defines your application sequence itself. And you can bring in or you can insert the spreadsheets having power information about the architecture that you're selecting, or the spreadsheet can be a kind of application sequence which is actually defined in a sheet as well. And when you actually run the simulation model, the reports actually provides information on both performance as well as power consumption. So this is actually helps you in understanding or performing the trade-off scenarios and try to compromise or try to optimize your architecture to meet both performance as well as power requirements there. To give you an idea over here, and here's the multimedia system platform, and here we have the hardware architecture at the top, including ARM processor with an hardware accelerator, Axi bus, and memories, things like that. And at the bottom I have the memory at the bottom I have my applications sequence, which is actually defined as a sequence of tasks that are actually running on the platform. For example, in this case, it actually gets the sensor, gets the data, or this image sensor gets the data, and it actually sends it off to the read frame and then decode frame, video post-processing, rendering, and things like that. And these blocks or these tasks are actually mapped virtually to the hardware platform, which is actually defined at the top. If you go inside these blocks, and here we have a concept of mappers, and these mappers actually allows me to map my incoming tasks or instructions onto the target platform. And once the target platform completes its processing, it actually sends the control back to the task itself, and it sends the control to the next task to proceed further. Okay, in this case what we are doing is we are actually going to model this multimedia system or run this complete sequence of tasks on the ARM subsystem core itself, and considering the system is running purely as a software part of my all these tasks as a software part of my system itself. So what I'm going to do at this point is I'm going to run the model, and I'm actually expecting about 13,000 macro blocks being processed under 20 milliseconds, and the power consumption of the system must be under 1 watt of power. And we have actually configured the model to generate power reports such as average power consumption. And here we have the power consumption report, and it actually tells me this is under 1 watt of power, and number of macro blocks being processed is actually somewhere near 6,600, and we were actually expecting 13,000. This actually tells me that not meeting the performance requirements, even though if I'm meeting my power requirements. So what you can do is we actually have seen the reports that are generated and identified that rotate frame is actually taking more CPU cycles, and so you can actually move this particular task over to an hardware accelerator. So hardware accelerator can process this particular task in a much faster way and try to understand what is going to be the performance versus power trade-off in this scenario. I just moved my rotate frame to hardware accelerator, and looking at the reports again, and initially the power consumption was under 1 watt, but after some time it started going up. So, but if you look at the number of macro blocks being processed, it is about 14,000 now. And the increased power consumption is because the hardware engine is consuming more than 34% of total system power consumption. So what you can do is you can actually introduce a power gating algorithm to make sure that whenever there is, whenever you're not running anything on the hardware accelerator, you can actually shut it down, or you can push it to a standby state or wait state or things like that. And looking at the report again, you can see that power consumption is under 1 watt, and performance is actually dropped about 20% or 12%. Still, performance is actually meeting our requirements, and also power consumption is meeting our requirements. This is how you can actually extend your model or conduct explorations to meet your performance as well as power consumption of a complete system platform as well. Okay. So looking at the energy consumption and analysis for a mobile platform, so here we have an example with an abstract level model of a mobile platform with PLLs and processors and modem and things like that. And in this case, we are actually computing power consumption based on the leakage current and voltages and fluctuations in the voltages using expressions. And we are not really relying on the state of that particular component based on how long you're running or how long you're processing in the platform itself. Okay, and if you look at the model for that, here I have the simulation model, and these blocks, actually we call it as hierarchical blocks, and each includes a certain set of expressions to try to understand what is the power consumption that has happened, and that particular computations are actually defined in the lookup table over here by looking at the device name and what is the state of that particular device. We will be actually utilizing these expressions to be able to compute power consumption of the complete system platform as well. And these way parameters allows us to kind of change the configurations and change the parameters for the system platform to be able to extend simulation analysis for our current requirements as well as future requirements as well. And here we have the reports, including instantaneous power and average power, and also looking at the battery discharge power as well. Okay, so here we have an example of IoT system, which actually has a harvester, a photovoltaic cell harvester, and we have the PMUs and battery, and also we have connected a lot of loads to this particular system, and also we have defined a certain set of workloads and use cases that runs on this particular hardware platform itself. And in the left-hand side, we have a certain set of lookup tables that actually defines the use cases and power profiles as well. And the reports that are generated includes looking at the charge and discharge cycles of the battery, which actually helps us in understanding the life cycle of the battery itself and try to understand how long that particular battery can sustain. And apart from that, looking at the lifetime energy consumption as well, which could be crucial or which could be interesting for most of the scenarios. And looking at this example in VisualSim Architect, I'm gonna move over to the tool, and here we have the tool, and here we have the photovoltaic cell power generator, and this actually generator reads the power information or gets the power information from these lookup tables for summer profile or winter or autumn or spring. And looking at these profiles, this actually includes information on a complete day information on power generation. For example, in this case, we are generating power between 12 a.m. to 7 a.m. In this case, we have provided as 0. May not be true in the real scenarios. And between 11 a.m. to 3 p.m., maximum efficiency of 80% power generation can be achieved. And similarly, this photovoltaic cell will generate power consumption based on these tables as well. And the workloads at the bottom actually allows us to define what are the different scenarios or different tasks that you're running on the platform itself. For example, if you are accessing your sensor, or if you are accessing if you're sending some data through your RF channels, or if you're doing any sort of processing based on the data that you have received through the sensors and things like that. And also we provided information on when you're starting that particular task and when you're stopping that particular task. You can sequentially start the task, or if you can parallelly execute all these tasks on the same platform to be able to explore the possibilities of running these architectural decisions as well. And looking at the automotive environment of generating power consumptions and looking at the resources that consume the generated power. So here we have the models for engine power generation or generators and transmissions and final drivetrain. And also we have consumers such as headlights, radios, radar and ECUs as well. And also in this model, we have actually modeled the processing units as a statistical models, which are actually modeled in these resource model FSMs. And when we actually run the model, This actually provides me reports such as application power consumption reports, as well as what is going to be the application response time if I run with a certain set of configurations. Okay, and looking at the energy or harvester for automotive requirements such as your motor related things, you can actually provide your information such as RPMs or durations and efficiency that you'll be generating. And also you can provide information such as what is going to be the maximum charge capacity that uh, motor will actually be generating or storing in a battery or things like that. Okay, so looking at the cycle accurate level power analysis, we actually provide a very detailed power model or performance model for a cycle accurate DRAM, and this is functionally and timing accurate. And the technologies that we support all the way from SDR to DDR, DDR2 to LPDDR4 memories, and you can actually quickly change these configurations with just the parameter values and things like that. And the power consumption capture can be referencing to a different memory banks or read or write requests, or changing the memory technology itself, and try to understand what is the difference between LPDDR3 with 500 megahertz to LPDDR3 800 megahertz technology or things like that. Okay, so here we have the power table, and in this case, if you see the power table for this particular memory, this is very detailed in this case, because here we are providing or capturing details such as standby state power consumption for active as well as write and read activities that are happening in the memory itself. And also we'll be looking at power consumption when you're actually running your refresh cycles on the memory as well. And this can be a text file or an CSV file that you can directly import into VisualSim as well. The kind of reports that you could get out of it includes the memory bank activities. This actually tells you which memory bank that you're accessing, and what is the power consumption that you're getting when you're accessing all the banks, or versus when you're accessing only 2 or 3 banks out of your memory block itself. Okay, so to give an example, here we have a model of dual channel DDR. In this case, we have the custom traffic generators models the read or write requests for the memories, which are actually connected across the AXI bus. And in this case, the DDR memory is actually configured for Micron 500 technology, and it can be changed to Micron 600 or 933 and things like that. And when I run the model, it actually provides me information on activities that are happening across the memory banks. For example, if I look into a particular region over here, for example, if I look at this particular region, when you have your activate signal, which is actually coming over here, this actually triggers your write request on the memory bank 1 itself. And so on and so forth. Other bank activities are also captured over here. Corresponding to that, we have captured the power consumption, both instantaneous and average power here. And you can compare this with when you're having a scenario in which you're accessing only one bank in your memory versus all the memory banks in your memory architecture itself. Okay, and going back to the presentation, so this concludes this presentation or the webinar. And the whole purpose of conducting early system level power analysis and performance analysis is to be able to capture the challenges that are involved in performance versus power requirements, and to be able to refine the system architecture to meet both the requirements as well, and also to model your energy harvest models and trying to understand what is the load requirements that a particular harvester can handle up to. And if you want to have a scenario in which you have to analyze your dynamic system performance or system power consumption, then you'll have to consider the dynamic activities that are happening in the component level and the system level, and try to understand how actually the dynamic behavior impacts on the total system power consumption as well as power performance as well as power requirements as well. And these system level models actually enables you to predict and eliminate possible design bottlenecks by inserting faults and errors into the simulation models at either at a hardware level or application level. So this actually provides you a broader picture of exploring your system architecture and making sure that the architecture works with the scenarios that you could not expect until and unless you implement the architecture itself. And in addition to that, you can distribute these simulation models across the development teams and customers using, you can actually export these models to an HTML page embedded with these simulation models, and people on the other side can run the model and read the documentations and try to explore the architecture and by changing the parameters and things like that to arrive at a particular decisions on whether the architecture is going to go with implementation or whether there are any kind of modifications required for the architecture what you have constructed itself.